So it's been quite a journey to be part of NVIDIA, working to build the infrastructure for AI for the past 15 years. So about a decade ago, NVIDIA introduced the first EDA system for deep learning. And last year, NVIDIA introduced the first rack-scale AI system called the GB200. So NVIDIA went from building a chip on a car to building a node with 8 GPUs to now building a full rack with 72 GPUs interconnected in a data center or across multiple data centers. The data center has become the new unit of computing, and networking is really the key here. So what started this amazing progress of AI was the confluence of three things: the new AI algorithms, the availability of large amount of data, and the invention of the GPU as a parallel computer. The AI model and the compute necessary has grown by 1 million x in a decade. The introduction of the transformer 3D supercharged processor. The compute capability or the requirement is increasing even faster than before. So the performance of the GPU has been increasing at an incredible pace. So for NVIDIA, from Pascal to Blackwell, over 5 generations of GPU in 8 years, the compute capability has increased by 1,000x. This is much faster than Moore's law, which is about 100x in a decade. But as you can see, even with this super Moore's law scaling, it's still not quite enough to keep up with the demand of the AI model that I described in the previous slide. Compute on a single GPU is not enough. We must scale performance across many GPUs. So AI training is a distributed computing problem. The GPU computes the error of the weight of the model, and the updated weights need to be communicated to all other GPUs. So there's communication associated with this weight update. But even within the 4 compute packs, the AI model might be too big to fit into a single GPU. So in that case, there's a significant amount of communication required between the GPUs if the AI model needs to be split across them. So as we split the model across more and more GPUs, more communication is needed. Many techniques have been invented to split the workload across multiple GPUs. And some of these require more communication than others. And people tend to use a mixture of all of these strategies. But whatever the technique, the fundamental trend is very clear. As the GPU performance increases, and as we employ more and more GPUs in the data center, the communication is becoming more critical. So let's take a look at an example of an AI factory. So here I'm showing a data center with 512,000 GPUs. In the case of Blackwell, each GPU is about 12,000 watts, for a total of 600 megawatts just for the GPUs. The Grace Blackwell system uses NVLink to connect 72 GPUs in an L1 domain in the rack. Each GPU has an NVLink bandwidth of 900 gigabytes per second per direction, or 1.8 terabytes per second by direction. The total NVLink bandwidth within the rack is 130 terabytes per second. So this is the scale-up network. These NVLink 72 systems then need to be connected with a scale-up network using optical interconnect. A 512,000 GPU cluster will require about 1.8 million optical transceivers. So let's take a look at the interconnect speed across 3 generations of NVIDIA GPUs. So the first row there shows the GPU HBM bandwidth. The HBM bandwidth per GPU went from about 2 terabytes per second in N-tier to 3 terabytes per second in Hopper, to now 8 terabytes per second in Blackwell. The second row is the GPU scale-out bandwidth. The SerDes speed went from 50 gig to 100 gig to 200 gig. And the GPU NVMe bandwidth, the total NVMe bandwidth per GPU went from 600 gigabytes per second to now 1.8 terabytes per second. The third role here is the scale-out bandwidth of the GPU. It went from 200 gigabits per second to now 800 gigabits per second. The scale-out network is usually connected with optical interconnect because of the distance required. So you'll notice as we go from local interconnect to increasingly remote interconnect, the bandwidth is reducing dramatically. In particular, the scale-out bandwidth is only about 1/10 of the scale-out bandwidth. So the scale-out network requires optics, which is very power hungry, expensive, and reliable. So its utilization in the AI network has so far been very limited. So let's take a look at the power of this optical scale-out network. So even with very limited bandwidth, the scale optics is already about 7% of the total compute power. And this is with roughly 1.8 million optical transceivers. Optics power doesn't scale as well as the compute power. Also in the future, the scale network might play a bigger role. So this percentage is expected to keep growing. Data centers are power limited, so any power you take away from compute will reduce the overall performance of the data center. So another drawback of optical communication compared to electrical communication is reliability. Here I'm just illustrating the cost of data center downtime. For a 512,000 GPU cluster, a 10% downtime would translate to roughly $3 million per day of cost. Optics isn't the only reason for the unreliability of the system. There are many reasons. However, optics, the reliability of optics is a major impediment to the wider deployment of the optics. So just to recap, transformers have accelerated the growth of model parameters and also the compute requirements. Data centers are expected to keep growing with this explosive demand. Data center is the new unit of computing, and networking is essential for the continuous scaling of the AI cluster. Today, the power, cost, and reliability of optics are major limitations to the construction of AI clusters. And this is an area which urgently needs new thinking. So Blackwell is the first platform to introduce 200 gigabit per second links for both copper and optics. The GB200 and GB300 NVL72 racks use copper cables to connect 72 GPUs on 18 compute trays through 18 NV switches. There are about 5,200 differential coax copper cables in the cable backbone. The total NVLink bandwidth is 130 terabytes per second. The scale-out network uses the LinkX pluggable transceiver with 200 gigabits per second per lane of DSP and Quantum X InfiniBand switch. Compared to previous generations, 200 gigabit per second SerDes require a lot more signal processing. The signal requirement is much harder to meet. The entire path from the package to the PCB, cables, and optics must be analyzed and designed to very stringent specs. So Blackwell introduced the first pluggable optical transceiver with 200 gigabit per second per lane. As I discussed earlier, the optical power is taking up a significant portion of the data center, and the trend is going up. And we believe co-packaged optics with silicon photonics will be the technology of choice for several reasons. So first, silicon photonics leverage the CMOS technology. So it makes it a very cost-effective solution for high-speed communication. It enables a very high level of integration and scalability. Co-packaged optics also increases the bandwidth density because very small connectors, like the MNC connector, can be used as a faceplate instead of very bulky optical modules. CPO also reduces the power significantly, and I'll talk about this more later. Because CPO integrates multiple components on a single chip, and there are fewer failure points, CPO also has the benefit of better reliability. So here we highlight several benefits of CPO compared to the traditional pluggable optical transceivers. So first, the signal integrity of CPO is much better. Instead of traversing through a long channel to the optical module at the front panel, the electrical signal of the CPO only travels very short distance within the package. And because of this signal integrity benefit, CPO power is also significantly lower because there's no need for very power-hungry DSP retimers. Compared to full retime optics, CPO is about 3.5 times lower power. CPO is more resilient against failure because there are fewer points of failure, and CPO is also actually easier and faster to install because the switch and the optics come tested non-split together. So a full retime pluggable optic consumes a lot of power. It is about 3.5 times more power compared to the CPO, about 25 watts versus 7 watts. So there's been a lot of effort to try to reduce the power of the pluggable transceivers by compromising on signal integrity. For example, TX retime optics, or TRO, removes the DSP on the receive side so that half of the DSP so it is a fine choice for the time being at 200 gigabits per second. Now LPO takes it one step further and removes the DSP completely, but LPO will be very challenging at 200 gigabits per second. It's not clear if mass production of LPO is feasible at 200 gigabits per second, and a way to alleviate that is to use what's called the co-packaged optics, or CPC. However, CPC is still an immature technology, and it actually requires a bigger package compared to the CPO. So now let's dive into NVIDIA's silicon photonics chip and explore some of the design choices. So NVIDIA will be the first to mass produce a microwave modulator. A more widely used modulator is the Mach-Zehnder modulator, in particular the traveling wave MZM. The biggest advantage of an MRN is that it's very compact. The diameter of an MRN is on the order of 10 micron, whereas the length of an MZM is on the order of several millimeters. An MRN requires a smaller driving voltage, and this is a big advantage for a standard CMOS process. It reduces the power significantly. The biggest drawback of MRN is that it's very difficult to maintain control because of the very high Q factor and because of the sensitivity to process and temperature. And this is where the design of the adaptive loop control becomes very critical for the enablement of the MRN. So now let's take a look at the optical coupling design choices. So here I'm showing two methods of coupling fiber onto the silicon photonics chip. On the left is surface coupling with grating coupler, which is what NVIDIA has chosen, and on the right is edge coupling. So surface coupling to edge coupling, to give an analogy, is like flip chip versus a wire bond. So surface coupling is 2D and enables a much higher I/O density. It is the grating coupler, the footprint of it is very small, and it also makes wafer level testing easy because fiber can be placed directly on top of the grating coupler. It is not so easy to do with an edge coupler. A grating coupler does have more loss, and this is something that needs to be taken into account in the overall link budget. Grading coupler is also easier to manufacture, but the biggest disadvantage of a grading coupler is that its optical bandwidth is limited compared to the edge coupler. An edge coupler is wideband. So this means that a grading coupler is not suitable for any optical technology which requires a wider optical bandwidth, like the coarse wavelength diffusion multiplexing, or CWDM. So NVIDIA has been working with TSMC for the past 4 years to jointly develop a silicon photonics process called COUP. So COUP stands for Compact Universal Photonic Engine. It is a 3D stack process with the EIC, or the electronic IC, stacked on top of the photonic IC, or the PIC. The EIC is in standard CMOS process, and the PIC is in 65 nanometer SOI process. This process uses a micro-lens design with grading couplers. We developed micro-ring modulators for this process, and there is also integrated metal heaters to tune the MRS. And finally, this process also integrates a high-speed photodetector. So let's take a look at the CPO packaging. So we use a detachable connector to connect the fiber onto the optical engine. The silicon photonics chip is soldered into the package, and the receptacle is assembled onto the silicon photonics chip. The optical connector, including the fiber array unit and the micro-lens array, can be detached from the receptacle. This detachable mechanism is critical in order to improve the yield of the fiber attach. So we use an external laser source for the optical engine. The advantage of using an ELS is that it's more serviceable in the field. We collaborated with the industry to come up with a high power and high efficiency laser, which has low noise, high yield, and very good reliability. There are several benefits of using a high power laser. First, it's more reliable because it reduces the number of lasers in the CPO system. It's also more cost effective because you need fewer PM fibers and fewer ELS modules. And finally, a high power laser increases the bandwidth density because fewer lasers occupy less space in the front panel. So to put it all together, we announced the NVIDIA Photonics product family in this year's GTC. It's a result of many collaborations with many ecosystem partners. It will be the first product to mass produce a micro-ring modulator, which is extremely compact and will enable very high bandwidth switch. We collaborated with TSMC over the last 4 years to jointly develop a silicon photonics process called COUP. We also collaborated with the industry to come up with a high power and high efficiency laser. We use a grading coupler because it provides a higher IO density, and a detachable fiber connector because it improves the yield of the fiber attach. So at this year's GTC, we announced the world's first CPO switch based on 200 gigabit per second SerDes. There are 3 liquid cooled systems that we announced. First, there is the next generation Quantum X InfiniBand photonic system with 115 terabit per second of total bandwidth, featuring 144 ports of 800G. There's also the next generation Spectrum X Ethernet photonic system, first one with 400 terabit per second of total bandwidth, with 512 ports of 800G, and the second one with 100 terabit per second of total bandwidth, with 128 ports of 800G. So these systems deliver 3.5 times better power efficiency, 10 times higher resiliency, and 1.3 times faster time to first training. And they're designed from the ground up for better reliability. We believe CPO will gradually replace pluggable optical transceivers and will become essential as we continue to scale the bandwidth of these systems. So now I want to show a video showing the inside of the Quantum X CPO switch. So that was, the CPU switch system that we announced. So let's now talk about the future. So there's been a lot of push to replace electrical copper wires with optics for a very long time. However, copper cable is still mostly preferred because of its lower power, lower latency, and lower cost. But as you can see from this chart, the reach of the copper cable has been reducing dramatically in spite of many innovations on DSP circuits. So at 400 gigabit per second, we're getting to a point where it's becoming impractical to build many systems. But notice that many things that copper is good at, like power, latency, and cost, are also the things that CPU is good at. CPU makes the transition from electrical to optical more compelling. We'll be talking about CPU as a replacement for the pluggable optical transceiver, but CPU is also the best candidate to replace copper cables eventually. So we're about to ship CPU systems based on 200 gigabit per second SerDes. So where do we go from here? The next natural step is to go to 400 gigabit per second speed. The industry is reaching consensus to use 200 gigabaud PAM4 as the industry standard for 400 gigabit per second. However, at this speed, without CPO, power and signal integrity will become a big problem. The only feasible pluggable option is to use full real-time optics. LPO and TRO, which I described earlier, will no longer be feasible. So if we don't go to CPO, we will be taking a big step backward on power in the next generation. So 400 gigabit per second CPU still has many challenges, and it will require the entire ecosystem to work together to become a reality. So after that, how do we increase the bandwidth per fiber even further? Optical BiDi is a good option to double the bandwidth without compromising on the radius. We can use polarization muxing to give another 2x bandwidth increase. We can use multiple wavelengths. However, increasing the bandwidth per fiber isn't always the best answer. We must strike the right balance between bandwidth per fiber, radix, and total throughput. So our first iteration of CPO puts the optical engine on the MCN with a switch die. So as we increase the optical engine bandwidth and the radix of the switch, the die-to-die interface bandwidth density and power overhead might start to become a big problem. Moving the optical engine onto the same silicon interposer as the switch die will help alleviate this problem. And this is called optics on interposer. It's also a natural solution for any optics technology which uses lower speed parallel data, such as DWDM and VCSEL, which I'll discuss more later. Now, one drawback with this approach is that the interposer size is usually more limited compared to the package. So the size of the switch that one can build with this approach might be a lot smaller. So let's now explore a couple of other optical communication technologies suitable for CPO. So far we've been focusing on one single wavelength with very high data rate. The alternative is to use a lot of wavelengths with each wavelength running at a much lower speed. The wavelength can be spaced very densely apart so that a large number of them can be used. This is called the dense wavelength division multiplexing, or DWDM. DWDM can potentially achieve better power efficiency because running the circuit at a lower speed is usually more power efficient. An example of achieving 400 gigabit per second per wafer using DWDM is to use a wavelength, for example, with each wavelength running at 50 gigabit per second. Because DWDM uses lower speed parallel data, optics on interposer is almost required in order to have enough die-to-die density. DWDM is very scalable with multiple options to increase bandwidth per fiber even further. So another alternative is to use slow and wide VCSEL arrays. Now run each fiber at a lower speed, it requires many fibers which are that need to be bundled together. So like DWDM, VCSEL array is most effective when combined with optical interposer because of the lower speed parallel data. Now VCSEL array is potentially more cost effective because VCSELs are very widely used. It could also be more power efficient because very simple low speed circuits can be used and there's no separate laser. The disadvantage of the VCSEL is that the transceiver heat must go down through the substrate instead of up to the heat sink. So thermal is potentially a problem. VCSEL reliability might be a concern at high temperature. So to summarize, AI data center is increasingly driving the roadmap for the photonic industry. The entire ecosystem is riding to this trend. The time for CPO has arrived. The bandwidth, power, and reliability benefits of CPO can no longer be ignored. We believe CPO will increasingly replace pluggables in scale-out networks and will become essential as the bandwidth continues to increase. We need to continue to push the envelope. There's a long roadmap ahead for CPO, and we need the entire ecosystem to continue to invest and innovate.